Picture a civilization so energy-hungry, it looks at a star and thinks, "Cute, we'll take the lot." Not just light, we mean the full nuclear fusion furnace. This is the Dyson Sphere idea: surround a star with collectors and have unlimited energy forever. But here's the twist. The moment anyone tries to make this real, physics walks in like a grumpy inspector asking tough questions. Where does the heat go? What's your structure made of? How do you keep it from drifting? And who approved the budget? Building around a star is a massive challenge. Freeman Dyson first introduced this concept in 1960. His paper didn't suggest building a perfect shell. Instead, he proposed that a civilization doing this would produce waste heat detectable as infrared radiation. This thermodynamic signature is still a key point today. You can't cheat entropy, capture massive energy, and you must re-radiate massive heat. If you're excited about the brutal physics behind civilization-scale engineering, remember to subscribe, like, and turn on notifications. Let's address a common misconception. A solid shell around a star? Probably not like sci-fi depicts. A rigid sphere is gravitationally unstable. Any slight shift creates uneven forces. The star won't stay perfectly centered. It doesn't magically self-correct. Without constant stabilization, it becomes an engineering nightmare. Now, a Dyson swarm, a vast cloud of independent collectors orbiting a star like an asteroid belt, can handle real orbital mechanics. Each unit follows orbital dynamics, can be adjusted, and can fail without collapsing the whole system. Just because something is possible doesn't mean we're close. It just means it's not forbidden by physics. Let's start with the simplest reality check: energy. The sun outputs about 3.8 times 10 to the 26 watts. That number is enormous and hard to grasp. Earth's entire energy consumption is tiny compared to that. A Dyson-level civilization isn't building a large solar farm. This civilization tries to intercept a significant portion of stellar energy and manage the heat it generates. Heat is the silent villain here. Every watt used turns into heat. Habitats, computation, propulsion, manufacturing. Everything ends as thermal radiation. In space, heat gets dumped through radiators. The cooler you want your systems, the more radiator area you need. Dyson projects focus less on harvesting energy and more on managing heat on a massive scale. This is why astronomers search for infrared technosignatures. For instance, Project Hephaistos analyzed millions of objects using data from various telescopes to spot mid-infrared signals that might indicate large-scale energy harvesting. Some candidates were flagged for further study, but none confirmed as artificial. Follow-up observations showed that some promising candidates were simply background noise, like distant galaxies glowing in infrared. Natural processes can mimic artificial signals exceedingly well. The universe is messy and loves false positives. Now let's consider the engineering side. If humanity tried to build a Dyson swarm, what technology would we need? The first missing piece is industrial scale in space. Dyson scale engineering assumes we can mine, refine, manufacture, and assemble things in space without hauling everything from Earth. Right now, even our largest structures are slowly built on Earth, launched in pieces and assembled. A Dyson swarm implies millions to trillions of units. That's not just a project, it's an ecosystem. NASA's on-orbit servicing, assembly, and manufacturing efforts show how complex servicing missions can be. Maintaining even one advanced spacecraft is challenging. Imagine maintaining 1 billion solar collectors being battered by solar storms. The second missing piece is autonomous in-space resource utilization. Launching enough materials from Earth is simply impractical. A serious swarm requires mining asteroids or inner planets, processing materials in a vacuum, and manufacturing structures in orbit. That's robotic mining, automated smelting, big fabrication, and self-directed logistics. Right now, we celebrate when a Mars rover survives a winter. We're not running space steel mills yet. The third missing piece is ultralight, massive-scale deployable structures. Solar sail research gives us insights into this challenge. NASA emphasizes that parameters like aerial density and membrane stability are vital. Thin structures wrinkle, tear, and warp under stress. Current research continues to improve how these membranes behave and remain stable in space. Small missions have shown just how fragile deep space deployments can be. If something as lightweight as a solar sail can fail due to minor issues, our margins are razor thin. A Dyson swarm would need kilometer-scale structures that deploy flawlessly, survive radiation, and endure thermal changes. The fourth missing piece is large-scale power transmission. Capturing energy is only step one. Moving it is step two. A swarm spreads distributed collectors over vast distances. That requires power beaming, likely using microwaves or lasers. Caltech's Space Solar Power Demonstrator successfully tested deployable structures and microwave power transmission in orbit. They proved the physics works on small scales. However, scaling from kilowatt experiments to stellar-scale power routing isn't linear. It's exponential. Beam control requires extreme precision. Receivers must handle intense power, and the whole system must avoid becoming an accidental solar system-sized laser pointer. The fifth missing piece is longevity and materials. Photovoltaic efficiency is improving. Research shows steady advancements in tandem cells. However, Dyson-level engineering demands more than just efficiency. It needs manufacturability from extraterrestrial materials, extreme radiation resilience, and self-repair capabilities. However, even if you figured out materials, manufacturing, power transmission, and thermal control, you still face governance. A Dyson swarm isn't just a machine, it's a civilization-scale infrastructure network. Questions abound. Who controls energy? Who settles disputes? Humanity struggles with homeowners' associations. A stellar energy grid would put those meetings to shame. This brings us to the Kardashev scale. A Type 2 civilization, according to Nikolai Kardashev, harnesses its stars' full energy. We're not even a Type 1 civilization meaningfully. We're still negotiating sustainability while celebrating small renewable gains. We need autonomous space industry to become routine. Self-replicating factories need reliability. Distributed control systems must coordinate across astronomical distances. None of these are single breakthroughs. They are systemic changes. And here's the humbling reality. A Dyson swarm isn't a completed project. It's endless maintenance. Components degrade. Orbits drift. Collisions happen. Software updates are ongoing. A Dyson civilization lives in a constant cycle of upgrades around a nuclear energy source. So, are Dyson spheres possible? A solid shell is dynamically unstable and thermally extreme. A swarm is feasible, but humanity is nowhere near building one. The gap isn't just a few decades, it's centuries of industrial transformation, assuming we tackle our current planetary challenges first. Currently, astronomers keep looking for infrared signals that suggest large-scale energy use inspired by Dyson's core insight. Modern sky surveys offer chances for systematic searches. So far, nature has proven more than capable of imitating science fiction. For now, the Dyson Sphere remains a thought experiment, a reflective opportunity for ambition. It challenges us to consider what happens when energy is no longer scarce. It raises questions about the kind of society capable of harnessing star-level power without collapsing under its complexity. It prompts us to wonder whether technological progress will lead to cosmic engineering, or if intelligence levels off beforehand. Humanity is still learning how to manage just one planet. Someday, perhaps far beyond our lifetimes, a civilization might dim its star in visible light and glow brightly in infrared, its waste heat gently radiating into the cosmos, evidence of energy mastery on a scale that is currently mythic. But until then, we're a species that can split atoms, land probes on distant worlds, live stream rocket launches, and still lose the remote control in our own living rooms. That's progress, just not Dyson progress. If that future ever comes to pass, it won't feel like magic. It'll feel like infrastructure. The breakthrough won't solely be in the engineering. It'll be in the collective discipline needed to handle that power responsibly. The real question isn't whether we can build around a star, it's whether we would be wise enough to manage one. For more grounded explorations of technologies that could redefine our cosmic future, subscribe, like, and turn on notifications. This is Tech Mythos.